Hello everyone. In the next 4 videos, we will cover the topics in the time domain analysis of linear systems. In this chapter, we will cover the following topics. The first one is the zero input response. And by the zero input response, we mean if you have a system and you have input and you have an output. Now, if there is no input, we want to know what is the output due to energy stored in the system, or in mathematics we say due to initial condition of the system. And that's what we mean by the zero input response. The second topic will be the impulse response, H of t. And that means if I excite this system with an impulse and I get an output that may look something like this, or it could be sinusoidal, this special output, we will call it impulse response, H of t. And that H of t basically will describe the system, and we call it the impulse response of the system. And the impulse contain many frequency content. So basically, the output will tell us how the system responds to the different frequency content in this impulse. The third topic will be convolution. And convolution basically, if I have the input x of t, and I have the impulse response H of t, then if I do convolution between them, I get an output and it will be y of t. And topic number 4, zero state response, is how to do the convolution to find the output y of t. And we call it zero state because the initial condition in the system, or the energy stored in the system, is 0. So the system response or the output is due only to the input. And the last topic will be system stability. How do we analyze the system based on H of t, the impulse response, and the characteristic root? How do we determine if the system is stable or not, especially internal stability? Okay, in this video we will cover the zero input response. And as I said before, zero input response means the input is 0 and the system is responding due to initial condition or energy stored in the system, and we call this the zero input response. When the initial conditions are 0 or the energy is 0 and there is an input x of t, then we call this output zero state response. If I add both output, then we get the total response, which is zero input response plus zero state response. So let's start with the zero input response. In the previous chapter or previous videos, we modeled this electrical system by this differential equation. And we modeled this mechanical system, or described the relationship between the input and the output, by this differential equation. This is the input, this is the output. Now, if the system is more complex, then it could be of a higher order, not just a second order. It could be of n order. And that will be the differential equation that describes a system of n order. Now, when we say zero input response, that means x of t here is 0. And basically, you ignore all these, and now you solve this differential equation. And in math, in differential equation course, we call this homogeneous equation, and the solution of the homogeneous equation, now we call it the zero input response. So how do we solve these homogeneous equations? And here D represent, just a reminder, a derivative. N is the order. N could be a third, 3, 4, 5, depend on the system complexity. Now, to solve these differential equations, we will assume a general solution for the output. And the output could be this exponential. Y of t is c exponential lambda t. Lambda, in differential equation, we used to call it eigenvalues. Here we will call it the characteristic root because it characterizes the system. Now, if we assume the output will be of this type and we plug it here and we take the n derivative of this output, n minus 1 derivative of this output, we will always get this again, and it will come out here again. Let me just show you the first derivative, lambda c. So now you have this again. If I take the second derivative, lambda square c e lambda t. So no matter how many derivative you take, you're always going to get this output back again, and we can take it outside the bracket. And if we do the n derivative, it will be this equation, lambda to the power n, a1, a2, and so forth. If I just do it for a second order differential equation, let's say d squared plus a1d, one could be a constant, plus a2, and y of t, we assumed it will be c e lambda t. If I do the second derivative of this one, which is here, it will be lambda squared c e lambda t, plus first derivative, it will be a1 lambda e lambda t, plus a2 times this, here is c, plus a2 c e lambda t equals 0. Now I can take these all out as a common factor, and I get lambda squared plus a1 lambda plus a2. This one here, this equation is a general equation for n order. This is just for a second order system. Now the question is, how do we solve this equation? You can say this is true if c is 0, but that is a trivial solution. And lambda, no matter what is lambda, the exponential cannot go to 0. So then the general solution is when these equals 0. So that means when lambda squared plus a1 lambda plus a2 equals 0, then we solve this differential equation, the second order. Or lambda n, this one, to solve the general n differential equations. Now this, we call it the characteristic equation, which is here. And the next step is, how do we solve this characteristic equation to find the possible value for lambda? If it's a second order system, then lambda here will have two possible values, lambda minus lambda 1 times lambda minus lambda 2 equals 0. So lambda can be either lambda 1 or lambda can be lambda 2. Either value will satisfy this equation, will solve this second order differential equation. This is the characteristic root for nth differential equation. So one possible solution then is c, we said y of t, we assume it is this value. So there is a possibility that it will be e lambda 1t. That's a one possible solution. Another possible solution could be c2 e lambda 2t. So the general solution could be a combination of these two possible solutions. So I'm going to put just a plus sign. And how do we find C1 and C2? We use the initial condition. Basically, what is the energy stored in the system? And you will be given, or in the lab you will be measuring, for example, what is the output at t equals 0? Maybe you find the 3. So that is one initial condition. Then you want to know what is the rate of change for this output, or the derivative at t equals 0. Maybe you will get -2. And that could be the second initial condition. And then you use these two initial conditions to find C1 and C2. And after you do that, you just finished solving the differential equation and you found the 0 input response, the system response due to the energy stored or due to this initial condition. So here, this is the general solution for n order differential equations. So let's identify some of the parameters. We said lambda 1, lambda 2, we call them the characteristic roots of the system because they characterize the system. And all these possible output or a combination of them, we call them the characteristic modes of the system. And all these constants, C1, C2, Cn, we define them using initial conditions of the system, or basically the energy stored in the system. So let's do this example. Let's assume we have this electrical system and it's described by these differential equations. And we want to find the characteristic equation, the characteristic root, characteristic mode, and the 0 input response. Well, to find the characteristic equation, we can just assume here y of t equals c e lambda t, and then plug it here as we did in the previous slides, and you will get lambda 2 plus 3 lambda plus 2 equals c e lambda t equal 0. Here we are asking for the 0 input response. So you set x of t to equal 0, so that is 0 here. And then the characteristic equation will be this one. Lambda squared plus 3 lambda plus 2 equals 0. And you will realize if you just replace d by lambda, you get the characteristic equation directly. Now to find the characteristic root, I have to factor out this. So I can say this is equal lambda plus 2 times lambda plus 1 equals 0. Now one possible value for why that make this equation true is lambda equal minus 2. Then that will be 0. And let's call this lambda 1. Another possible value when lambda is minus 1. That will also make this equation 0. So another possible lambda 2 equal minus 1. So the general solution will be combination of these characteristic mode. C1e minus 2t, that's lambda 1t, plus C2e lambda 2, which is minus 1t. And this is y of t. That's the solution. And the characteristic modes are these. The characteristic roots are these. Are we done? No, we need to find what is C1 and C2. So we're going to use this given initial condition. Y at t equals 0 is 0, and the derivative of the output or the rate of change at t equals 0 is minus 5. So let's take the first initial condition. Y at t equals 0 equals C1, plug for t here 0. E minus 2 times 0 is just 0. Plus C2, plug for t here 0, so that e to the power of 0 is just 1. So this is just C1 plus C2. And this equals 0. So that's equation 1. Let's call this equation 1. Now let's use the second initial condition. The derivative at t equals 0 is minus 5. So let's take the derivative of this one. So that will be y prime of t equal. If you take the derivative of this one with respect to t, it's minus 2 C1 minus C2. Now if I plug for t0, it will be y prime 0 minus 2c1. Plug for t0, that's all 1, minus c2. Plug for t0, that's 1. It's equal minus 5. If I multiply everything by minus 1, that will be just 2c1 plus c2 equal 5. And that's my second equation. Now I have two equations and two unknown, c1 and c2. If I use these two equations from here, C1 equal minus C2. So if I plug for C1 minus C2, I get minus 2 C2 plus C2 equal 5. And from here, C2 equal minus 5. And now C1 equal minus C2, so that C1 equal minus times minus 5 is just 5. So the final solution, I plug for C1 its value, which is 5. I plug for C2 its value, which is minus 5, and that's the solution. Y of t equal 5e minus 2t. C2 is minus 5e minus t. And that's the solution. If we plot this solution, that's the plot. This is y of t, and this is time, and the plot of this equation is this one. So the system here, it could have some input. Then at t equals 0, I shut off the input. But there is some still energy in the system. For this electrical circuit, there probably some energy in the capacitor and in the inductor. So even though there is no more input, but the current, the output y of t, still will have value, even though I shut off this system. So now the capacitor and the inductor will start releasing the energy, and when we solved it and we plot it, it looks like this negative, then it goes back. That means if at t equals 0, if I shut this input, x of t is 0, the current will go like this now, negative direction from the original, and it will go really high all the way to minus 1.2, then it started decay. Why it started decay? Because now the current, all the energy will be absorbed by the resistor. Electrons flow this way, current flow the opposite direction of the electrons, and the electron will flow and bombardment with the resistors, the atoms, and heat will be generated here. So the motion of the electron will be lost to heat across the resistor, or if this was light, it will turn the light. And it will be like this. And the initial conditions here, it means at t equals 0, the current was 0 the moment you shut off the system. Y prime 0 equal minus 5, that's the slope. So this is the slope. If I clean this a little bit, that will, and enlarge this, that will be the slope here, is minus 5. And that's the meaning of these mathematical equations and symbols in a physical system. In this case, it was electrical system. Now, what happened if there are repeated characteristic roots? So when you got the characteristic equations, you factor out lambda, you find that lambda 1 equal lambda 2 equal lambda n. So if it was like a second order and you factored it out, and you find lambda 1 equal lambda 2. Now what's the solution? C1 e lambda 1t plus C2 e lambda 2t. Is that the solution? Well, even if you use the characteristic equation and you find C1, C2, it will end up just e lambda t if lambda 1 equal lambda 2. But that's not a complete solution. That could be a possible solution. But a general solution is you should say y of t, if it's a repeated, it's like a function called g of t time e lambda t. And g of t could be t, it could be t squared, it could be t cubed. And if you plug these possible solution in these polynomial equations, if you plug it here, as we did here, and you solve for g of t, you will find that it could be t, it could be t squared. And we did that in differential equation. It's out of the scope in this course, but in general, for repeated roots, you will always find the t. So if it's a second order, like this case, and it's repeated root, then the solution will be y of t, c1 e lambda t plus ct e lambda t. And this is c1 and this is c2. If it's a third order system, and all three characteristic roots are the same, then the solution will be C1 e lambda t plus C2 t e lambda t plus C3 t squared e lambda t. And for n system, that would be Tn minus 1. Third order, you get t squared. And that's the general solution for a system with a repeated characteristic root. That means the characteristic roots are the same. Let's take an example to solve this system. So to find the characteristic equation, just replace d by lambda. So that will be lambda squared plus 6 lambda plus 9 equals 0. Now to find the characteristic root, factor it out. This will be lambda plus 3, lambda plus 3 equals 0. And this will be lambda 1 equal minus 3, lambda 2 equal minus 3. So now we have repeated roots. So the general solution is y of t equal c1 e minus 3t plus c2 t e minus 3t. And now we need to find these constants C1 and C2, and we're going to use these initial conditions. Let's find the derivative. Since one of them we need to have the derivative. So the derivative of I of t equal minus 3 C1 e minus 3t, and the derivative here you just use the chain rule. So that will be plus C2 e minus 3t minus 3 C2t e minus 3t. Okay, so now I can use this initial condition in these equations. So that will be y of 0 equals c1 plus, you plug for t0, that's 0. And it's equal 3. So from here, c1 equal 3. Now let's use the second equations, which is the derivative at t equals 0 is minus 7. So let's plug here t equal 0. And this will be y derivative 0 minus 3c1. You plug for t0 here, you get 1. Plus, plug for t0, you get plus c2. Plug for t0 here, you get 0. And this equal minus 7. And that will be minus 3c1 plus c2 equal minus 7. Now plug for c1, 3. So that's minus 3 times 3 plus c2 equal minus 7. And here c2 equal minus 7 plus 9 equal 2. So the final solution then will be, you go back to the original equation here, and y of t, plug for c1 3, that's equal 3 e minus 3t, plug for c2 2 plus 2t e minus 3, and that's the answer. Now I have a question. When you solve for the characteristic root, like in this case came here, repeated root. In the previous example here, when you solve for the characteristic root, it came -2 and -1. Is it possible that you have a characteristic root that is positive number, like +2, +4, +5? Mathematically, it's possible. I can give you here an equation where lambda is a positive. But for system analysis, for a stable system, that's not possible to have a positive characteristic roots. Because look what will be the characteristic mode. It will be C2E, if lambda, for example, positive 3t. You can't have this output. Why? Because with time, this will just grow. Maybe it's going to be something like this, to infinity with time. If y of t is current, that means the current will go to infinity and the system will burn. Capacitors, resistors, before even it go maybe to 5-6 ampere, depend on the system and the parameter. So that's not possible. That's not a stable system. Mathematically, it's possible for system. If you find a characteristic root that is positive, that is not stable system. The output is just gonna be huge. If the output was a mechanical system and y is a speed, that means the speed with time would just go to infinity, or y of t is a force, the force will go to infinity. Where are you going to get this energy? It doesn't make sense and it's not possible. So when you solve these problems, if you get positive lambda, go back and check where did you go wrong, if it's stable system. Same thing here. In repeated root, it's the same way. You're always going to get lambda negative. Now, you may think in the output there is t, so it grow with time, and then with time, as time pass, t will get larger and the output y of t here will get larger. So where is this energy is coming? Actually, this exponential decay at faster rate than the growth of t. So if t is growing this way, then this decay at faster rate like this. So when you multiply t times this exponential, you multiply this times this, you will eventually get exponential decay. So this eventually with time will go to 0. All right, so far we learned first example where lambda 1, lambda 2 are distinct real numbers. And also we learned how the solution will change if lambda 1 equal lambda 2. We have a repeated roots. The third possibility is when lambda 1 and lambda 2 are complex roots, like they may equal sigma plus j omega, where sigma could be 3 and j omega could be 2, something like this. Okay, in this case, lambda 1 here, lambda 2, lambda n could be complex, and let's say it's lambda 1 equals sigma plus j omega. Now we know for sure the output y of t has to be real, and for that to be the case, then you have to have another root that is a conjugate of this complex root. So if you have a second order, you will have two characteristic root. They will be conjugate of each other. So lambda 2 then will be sigma minus j omega. That's the only way when you solve for the zero input response, you will end up with a real signal. So if I have a second order system, I have lambda 1 and lambda 2, then the general solution y of t will be c1 e lambda 1, which is sigma plus j omega t, plus c2 exponent lambda 2, which is a conjugate, sigma minus j omega t. This is the general solution. So this is the characteristic root, lambda 1, lambda 2. Now you can use the initial condition to find c1 and c2. But if you solve it in this form, you will deal with so many complex operations, adding, subtraction, dividing to find c1 and c2. So better we simplify this solution to a form that doesn't have complex number. So let's do that. So y of t equal c1 e sigma t plus e minus j omega t. Now I can take e sigma t here out as a common factor. So then I have c1 e j omega t plus c2 e minus j omega t. Now we know this is a real system. So y of t has to be a real signal. And the only way for it to be a real signal, when you solve for c1, c2, if they are real numbers, then they will be equal. if C1 become a complex number, then they have to be conjugate of each other. So let's take the general case that C1 and C2 are complex number when we use the initial condition. Then they will look like this: E sigma T. C1, I can express it as C E J theta. That's a complex number in polar form. E j omega t plus C2 will be the conjugate of C1. So that will be C E minus j theta, E minus j omega t. And now I can take C out. And this will be, I can combine these. Plus, same thing, combine these. Now I can divide this by 2 and multiply this by 2. And let's call these 2C a different symbol. It's still going to be a constant, so let's just call it C0. And this now will become a cosine. And that's the solution. The output, if the characteristic root are complex, will be in this form. You use the initial condition to find these two constant, C0, or I can call it C back to here, so that looks like this, C0 or C, just a constant, and theta. And the characteristic root, sigma, will be this, and omega will be this. So now the output, if I plot it, it will look something like this, where sigma will determine the decay rate, and omega here, the oscillation rate, and C, 0 or C, is just be the amplitude, and theta, how delayed this way. And that will be the zero input response for a system with complex characteristic root. Let's take an example to find the zero input response for this system here. Okay, let's find first the characteristic equation. So that would be lambda square plus 4 lambda plus 40 equals 0. And here I can find lambda using this quadratic equation, where B, this is B, 1 is A, B is 4, and C equal 40. And if you solve this one, then you will find the two possible values for lambda 1. It will be minus 2 plus J 6, and lambda 2 equal minus 2 minus J6. So then the solution, y of t, will be a constant C, E sigma t, that will be minus 2t, cosine omega, which is 6t plus theta. This is sigma, this is omega. Now I need to use the initial condition to find C and theta. The given initial conditions are the output at t equals 0 is 2, the derivative at t equals 0 is 16.78. So let's find first the derivative. So derivative of y with respect to t is C, use the chain rule, minus 2e minus 2t cosine plus theta plus C e minus 2t. The derivative of the cosine is minus 6 sine 6t plus theta. Okay, now let's use the initial condition. First initial condition, if I plug for t0, it should equal 2 according to this. So that will be y0 equal C, plug for t0 here, that will be 1, cosine, plug for t0, that will be 0 plus theta, so that's cosine theta, and this equal 2, and that's my equation 1. Now let's plug for t here 0, and they said the derivative will be 16.78. So then y prime 0 equal, plug for t0, this will be C minus 2 cosine theta plus, plug for t0, that will be C times minus 6 sine theta. So that is minus 2 C cosine theta minus 6 C sine theta. And these equal 16.78. And that's equation 2. Alright, now we need to solve these two equations to find C and theta. One way to do that, let's use equation 1 to define C. So C will be 2 over cosine theta. And now I'm going to replace the value of C here and here by this value. So then I will have minus 2 over cosine theta times cosine theta minus 6 and replace c by 2 over cosine theta times sine theta equals 16.78. And this is just minus 4 minus 12 sine theta divided by cosine theta, you get tan theta equals 16.78. And this will be minus 12 tan theta equal 20.78. And I can solve now for tan theta equal 20.78 divided by minus 12. Now, be careful. If you use your calculator to calculate these, you will get like minus 1.047 radians. But theta this is opposite divided by adjacent. That means opposite is 20.78, so that's theta, and adjacent is minus 12. If you find this theta, but it's not the same here, this is what we are after. This is theta, so let's call this theta bar. So but if I use the calculator to find theta, tan inverse 20.78 over 12, I'm finding these. And if you do this, you will get 1.0478. And then this theta, let's call this theta bar. So theta now will be this angle, which is 180 minus this. So that is pi minus 1.0478. This is radians, not degree. So that will be 2.094 radians, or equivalent to 120 degree, which is 2 pi over 3. Now let's find C. So now I will go back to this equation to find C. So then C will be 2 over cosine, either if your calculator in radians, you plug here. If your calculator in degree, you plug this one. So let me use radians, 2.094, and the answer should be minus 4. So our final answer, then you just plug the constant here. This is minus 4 and theta is 2 pi over 3. So it will be y of t equal minus 4 for C. E sigma is minus 2t. Cosine omega is 6t, and theta is 2 pi over 3. And that's the final answer. And this is the final answer. So to find the zero input response, you find first the characteristic roots. There are 3 possibilities. They could be distinct real. Then the solution will be C1 e lambda 1t plus C2 e lambda 2t. Second possibility, lambda 1, lambda 2 are repeated root. Then we say it will be C1 e lambda t plus C2 t e lambda t. Third possibility, they are complex root. Then the solution will be C e sigma t cosine omega t plus theta, where the complex root, the real part is sigma and the imaginary part is omega. Sigma decay rate, omega oscillation rate. Now, when we find the zero input response here, we assume the system could be running for a while. Then at t equals 0, we opened it. So no more input. X of t is 0. Then the energy stored in the system will start be dissipating, and it will generate an output. And that output is the zero input response. So the t, the instant I close the switch or I open the switch, I can represent right before closing the switch by 0 minus. That means nanosecond before the action of closing the switch or open the switch. And 0 plus means nanosecond after the action t equals 0. And the action could be opening the switch or closing the switch. And these simple, that's what they means. And also, if you think of mechanical system, just think of the following. You have here a spring, you have here a dashpot, and you have here a mass. And then you have here a force pulling it. So I'm pulling this mass. And at t equals 0, that could be 12 noon, I let it go. I let my hand go from pulling this mass. Now there is no more force, no x of t. What will happen to this mass? It may go back and forth until it settles maybe here. That motion is what we call the zero input response. All right, this is the end of this lecture or this video. And next video, we will be discussing the impulse response H of t. How do we derive it? Thank you.